Hello. Today, I want to talk about piecewise functions, explain what they are and how they work. So our goals after this video is to be able to graph, you should be able to graph and evaluate piecewise functions, and then also be able to find an equation of a piecewise function given its graph. So first off, let's explain what a piecewise function is. It says below, a piecewise function is a function made of pieces of other functions, as the name suggests. Example, and so before we get to the example, so it just sounds like as the word implies, a piecewise, we take functions, parts of functions, and kind of stick them together. Now we do have to take careful about how we're sticking them together, but that's the basic idea. So what we have to do then is for each, essentially around splitting up any domain, maybe all real numbers into certain parts, and we have to define over a certain part of that domain what the function looks like. And we have to write that out. So let's look at an example. One example is an example you've hopefully seen before, the absolute value function. And hopefully you're familiar with a graph that looks like. It can also be written like this. So in fact, let's come over here to the right. Okay. So as it says, the absolute value function can be written as the usual way, f of x is equal to the absolute value of x, or as it shows right here, we can also write it as a piecewise defined function. I'll just rewrite this. So it's going to be, it looks like the function x, the identity function, if x is greater than or equal to 0, and then it looks like negative x if x is less than 0. So what we're going to do then is graph this. So give me a moment to pick a graph, and we'll actually show the graph of this and how this works. And I need to change the setting, so bear with me a moment. Okay. And for some reason, sorry. Let's try that again. For some reason, it went to the, I think I know what happened. Okay, there we go. So let's graph this absolute value function using this piecewise definition. Okay. So it says looks like x if x is greater than or equal to 0. Okay, so one thing about a function evaluation, okay, help us out. So for example, if f of 0, what's f of 0? When we look over here, plug in, this is that part of the domain, x is greater than or equal to 0. That includes this. So f is just 0 is just 0. Make that 0 look better. Or give me a moment, I'm having something weird going on with the. Let me try that again. F of 0 is equal to 0, of course. You can get that from either one, but also if we plug it in. So which part of the domain is 0 in? Well, here it's an x is greater than or equal to 0. That includes this. It doesn't include this one. X 0 is not part of this section of the domain. So you plug it in here, and it says that's going to be 0. Okay. Now, something like f of 1, same thing. 1 is in this part of the domain. It's greater than or equal to 0. So it's also 1. What about f of negative 1? F of negative 1, well, negative 1 is in this part where x is less than 0. So it says, according to that, negative 1 is going to be negative. It's part of the negative. And then x itself is negative. Oops, should be negative 1. And so that's going to be positive 1. So what happens then if we graph this, we just found that f of 0 is equal to 0. F of 1 is equal to 1. This graph is a bit small. F of -1 is equal to +1. And what you get is that V-shaped form you saw, or you've seen before, with if I draw it well enough, of the absolute value function. So we can use either this definition or also this definition. So once again, what we do then to evaluate it or to draw it is determine which, for each x, which part of our domain we're in, and then plug it into the appropriate function. Now, I want to caution you about a couple things regarding functions in this way. So once again, let me come back here and let me give you the graph of a function, and we'll show what some issues you can have with trying to make functions this way. So remember, a piecewise function, you have to take some care in defining it because it still has to be a function. Let's imagine something simple, a simple function, maybe just made up of two horizontal lines, two constant functions. Let's say we had this function here. So for this section, it looks like this. Okay, so to write out what that should be, that would be f of x is equal to what I've done here would be for it's going to be equal to 4 if x is greater than equal to 1, and it's going to be equal to 2 if x is less than or equal to 2. Now, hopefully you can see a problem there. Of course, this is not a function. Okay, this fails the vertical line test. The vertical line test says if I draw a vertical line through it anywhere, if it intersects, it's not a function. As we see, the problem is for a function like this, the question is if I want to do f of 2, okay, well, actually f of 2 has two different values, 2 and 4. Okay, and the same actually for 1 as well. That's a problem. So you have to be careful about how you're defining it. Or let's look at another example. Even if we do something a little more subtle, let's make another graph, and this actually let me move it to the side where we have a little more space this time. This time let's do a similar one. Let's say I try to fix that problem. And let's say this time I have f of x defined this way. And so it's going to be 4 if x is greater than equal to 1, and 2 if x is less than or equal to 1. Now, up to this point, you may still see a problem. Let's see. So if we graph this, the first part, x is greater than equal to 1, it's going to be 4. Okay, so right here, I'm making a closed circle because it's included at 1. That's the top part of this graph. Now, let's draw the second part. Now, it's equal to 2 if x is less than or equal to 1. Once again, here x is less than or equal to 1. And I have to include this point where x is 1 because it's included because the or equal to part. And it looks like this. You see, once again, though, that's still not a function. It still fails the vertical line test. Oops, not a function. This fails the vertical line test. Only at just one point, but at x equals 1. Okay, so what happens there, as you can see, is that even though it's just at one point, because both these points are included, then this is not a function anymore. Now, I could fix that. Let's actually go down to the next page. Let's try this again. Let's actually fix that. Let's make something actually is a function. Let's go back over here. So let's try this one more time to come up with something that is a function. So I would do f of x is equal to this time to 4 if x is greater than equal to 1, is equal to 2 if, but this time let's put it as x is less than 1. Okay, let's make sure that works. So when x is greater than or equal to 1, so starting here at 1, it's going to be 4. And once again, we're including 1. This x is greater than or equal to 1. So this point here is included. So that's the top part of the function. Then bottom part of the function at 1, because this time we're saying 1, that point at 1 is not included. So the point 1, 2, we put an open circle there indicating it's not included. And this time, this is a function. We've eliminated that problem, okay? This time, this point is only included. So for example, in this case, f of 1, what would that be? So f of 1, figure out which part of your domain you're in. It's not x is less than 1. That's not true, but x is greater than or equal to 1. That's true. So this is going to be 4. Or in the case up here, if you did f of 1, you would have had 2 outcomes, 4 and 2. Here, this is now correct. F of 1 is only 4. Okay, and that also gives you an idea of function evaluation and graphing piecewise defined functions. So let's do another example. I think I can fit another one in here. Let's graph okay, give me a moment. Let's decide for sure which one I want to do. Okay, let's graph this. So, oops, f of x is equal to 2x minus 1 if x is less than 2, and x plus 2 if x is greater than or equal to 2. So like we saw that last example, we've been careful here not to include 2 in both parts of our domain, so this will be a function. You'll see both these are equations of lines. This is going to be a piecewise defined function. So how can we do this? Well, once again, let's create a graph. And I might try and enlarge it slightly if we can. Okay, that's better. Now let's take a look. So without going into a lot of detail about something you may have studied in other videos or other classes, let's take a look at this bottom graph. Okay, so this is a line, straight line. This is in y equals mx plus b form, slope-intercept form. The slope is 1. The coefficient in front of x is 1. The y-intercept is 0, 2. So on this graph, well, let's see. Let's actually move this over just a bit. I need some space. What I said was true, but what we may have to do then is we have to think about this a little bit different way. So for starting point, let's take the bottom one. So let's do f of 2, since that's our boundary point here. That's our starting point. Okay, f of 2. So once again, it's going to be this part of the evaluation, plug in 2. Since 2 is less than or equal to 2, that's true. 2 plus 2 is 4. Okay, so we know one point on this line, 2 and 4 right here. And since it is or equal to part, that's included. This point is included here. Okay. Now, let's do another point on that line. How about we do f of, let's do one more point. How about we do f of 4? Okay. So f of 4 would be on this same region of our domain. Plug in 4 plus 2 is 6. So 4 is going to be 6. Okay. So this is a straight line. All we need are 2 points for a line. So this looks like this part of it. Okay. Now let's think about, oops, I forgot to write in the answer. Think about the other part. Now here, actually make this 4 look a bit better. We actually look like a 4. Now, what if we did f for the upper half, Let's also think about this. So here, remember our graph starts, it doesn't include 2, but essentially ends there at 2. So let's think of it this way. So for the upper function, let's actually do f of 2 there. Now this point won't be included, but it will give us an idea of where this essentially our open circle should be. Okay, if we plugged in 2 here, 2 into this, we'd have 2 times 2, which is 4, minus 1 is 3. So 2, 3, okay. Once again, this is not included in this part, but it gives us an idea where our open circle would be. Once again, I plugged in 2 here. So 2 times 2 is 4, minus 1 is 3. This part, if we go up to 2, 3, there'd be an open circle right here, okay, for this graph. That's its ending point for this part. And then we need one more point on the line. So for this one, since it's in slope-intercept form, we can say our y-intercept is going to be -1. Okay, 0, -1, which is down here. And so we need 2 points for a line. So this part of the graph would look like this. Okay, so that's what our piecewise defined function would look like. Okay, now with piecewise defined functions, you can have gaps, vertical gaps like we have here. You can also have horizontal gaps. You can have many kinds of gaps. They don't always have to line up or always have to meet, have to be continuous in any way. This is valid. Okay, this is one way to graph. So to graph a piecewise function, you can also use piecewise functions other than lines, any kind of graphs. And basically, then figure out your graph, determine your graph for the part of domain you're doing. Then also, you may have to include points like this, which is not actually included on the graph, but actually then help you to graph it and help you to figure out the extent of your line. Because although this part of the graph doesn't include this exact point, it includes everything less than 2, like 1.99999 for x. Okay. All right. Let's do one more example. This time, let's actually start with a graph and want to be able to write down the piecewise defined function. Let's take a look at this. Our directions will essentially be then to find the piecewise function. I'll just say from the graph. And the graph I'm about to paste. Let's paste it right here. Okay. I need to change the setting so I can move it around. There we go. Now, let's move this up here. And also, let's enlarge it a bit so we can see it better. Okay. Let's take a look at what we have. Now, let's see if I can identify what each graph is. So the upper graph, let's call it the upper and lower. So the upper graph, hopefully you recognize that. We've seen this function before already. That's actually the absolute value function. Okay, because it goes to 0.00, although it's not indicated. It goes to 1, 1. It's not included, but goes to 1, 1, and then -3, 3. And it has basically kind of a corner right here. So this is the absolute value function. The upper graph is f of x equals the absolute value of x. Okay, now, what part of the domain is that upper graph? What's its domain? Let's take a look. So it shows us then, of course, it goes forever in this direction. So it comes in from -infinity to the left. That's how far to the left it goes. And to the right, it comes up to 1. Okay, but it doesn't actually include 1. So we use parentheses there to indicate it doesn't actually include 1. Okay, another way to say that, and we say or, another way to say that is x is less than 1. Okay. Now, let's look at the lower graph. The lower graph will take a little bit more work. First off, we have to get the domain. That's probably going to be a bit easier. So in this case, our domain, so how far to the left and right does this graph goes? Now, it doesn't go all the way to infinity. We can see that. It starts at 1, left endpoint, then it goes to +4. As we can see, both points are closed in circles. Both are included. So we use brackets here. Or we can also write that as 1 is less than or equal to x, which is less than or equal to 4. Okay. Now, as far as what graph it is, it's a straight line, which means it looks like y equals mx plus b. Now, without taking the time to do that, basically what you would do, you're given 2 points on the line. You can find the slope of the line using those 2 points. Then also, you can also take one of the points once you find the slope, it's define m. Then once you have your m, take either point, plug it in for y and x to find b. So I'll go ahead and tell you, so this is going to be, the equation of this line is going to be y equals negative x plus 1. So our piecewise defined function, also let me go back and change, let's write this as up here as y equals x. So I can write then f of x as the entire piecewise defined function. Okay, so upper graph, then we said, it doesn't matter which one you consider right first, top or bottom, but I'll start with that one. So the upper one, this one is going to be the square root of x if then our domain x is less than 1. And then our second one, we said was the graph of negative x plus 1 if x is between 1 and 4, including 1 and 4. Okay, so when you're going from a graph to a piecewise defined function, make sure you determine in each case what kind of a function it is, okay, in each part of your domain, and then figure out the extent of your domain, okay, in both cases, or how many cases you want, and then write that like that. And it also doesn't matter which one goes on top, which one goes on bottom, as long as you have the correct part of the domain with the correct function. And also you can have as many kinds of functions you want, piecewise defined functions, not just linear functions. And you can also have as many pieces as you want. You could have a piecewise defined function with 10 pieces, where you could have 10 different functions for 10 different parts of the domain, for 10 different parts of the real line. It's up to you. But so what we learned so far then today is we learned what piecewise defined functions are, okay, what they mean, how to graph them, and also how to understand their domain, also how to evaluate them. Thank you. Have a good day.